Okay, great. Good to see you all again. So this is my second lecture, and I'm going to continue by this time talking more about direct detection. So my goal for this second lecture was to discuss some more this way of thinking about the rates in terms of target response and dark matter kinematics, and then use that to motivate why so many people have been thinking about bound systems and condensed matter systems as a specific case of bound systems, which I mean, we're not thinking of free target nuclei, we're thinking of bound nuclei and ions. So there's a lot of condensed matter in this topic, and so my goal is just to hopefully put some broader framework on this that makes it a little bit more understandable than thinking about specific materials that you often see if you start diving into this. But if you do want to get into more specific materials, etc., I'll mention again this review that we've been working on that will actually come out next week, likely, on the Aug5. All right, so to start off, this was the rate that I mentioned for dark matter scattering that I tried to be fairly general about this rate in a direct detection experiment. And so I split it up into a few different pieces that we've been thinking about. Of course, this first part is this dark matter astrophysics aspect of the velocity and number density. This second piece was what I've been calling the dark matter scattering kinematics. So it's just the phase space for momentum and energy deposition, subject to the energy conservation for the dark matter itself, which, if we're talking about halo dark matter, that resulted in these regions, parabolas, in momentum transfer and energy deposited, where this was roughly mxv, and this was, well, this was mxv, and this was 1/2 mxv squared. So of course, the dark matter scattering is not really equally weighted inside this region. There's going to be different weighting depending on, for instance, this interaction strength we'll get to shortly, but this at least tells us the allowed kinematic region. Depending on your model, you might actually prefer to live here or over here, and that's dependent on your model. Okay, so that's just kinematics. This part is the particle physics model. Well, other parts can also contain aspects of the particle physics model, but this is really the particle interaction strength squared. And I'm going to return to that shortly because there's a couple definitions I missed in the previous lecture. Okay, so that gives us some information about how we should weight this phase space. And then the last part was what I called a dynamic structure factor, which only depends on the target system. This kind of notation is not universal necessarily in the literature, but I'm using it because it's something that does appear a lot in the condensed matter literature. And it kind of puts everything on a similar footing by just talking about what is a given operator you're looking at and how does the target respond for that operator for a given momentum transfer and energy deposition. So the example I gave last time was for 3 nuclear recoils. Even though this is not the language it's always used, you can also write down a dynamic structure factor, which will just have this free nucleus dispersion inside of it. So that just comes from taking the energy conservation bit and saying initially the nucleus has 0 energy, and after the recoil, it has q squared over 2mn. So that looked, depending on what the nucleus mass is, that would look like a resonant response on this dispersion. All right, so to say a little bit more about this particle interaction strength, last time we also talked about one of the motivating, some of the motivating benchmarks for sub-GeV direct detection. Emphasize this part some more. And so we've been talking about dark photon mediators. As a way to get both freeze out and freeze in of sub-GeV dark matter. So as a reminder, we had freeze out if the dark matter mass was above 10 MeV. And we had freeze in. The dark matter mass was above about 10 keV. So these are really well-motivated dark matter benchmarks. The first one corresponded to the heavy mediator limit, which means basically the dark photon mass was somewhat larger than the dark matter mass itself. That's the question.
Yeah. Are there models in which some kind of particle freezes out at early times and then somehow freezes back in?
Yes, there are definitely models with kind of mixed freeze out plus freeze in. Yeah, there are those kind of multi-component dark sectors. So I can't think of a particular reference off the top of my head, but I could probably find one after for you. Yeah, if you're interested, yeah. Yeah, so these are definitely the simplest models. There are way more. The other one was freeze in, and as I was saying, we were mainly looking at freeze in as a well-motivated model for the light mediator limits. And there, the dark photon mass is going to be much, much smaller than the dark matter mass in general. And so that has consequences for this interaction strength. Oh, yes, question?
Yeah. Yeah, so we've been discussing the dark photon as a mediator, but I also heard that dark photon has been proposed as dark matter itself. In this case, is the discussion very different to what we've been saying in the lecture? So
yes, something I wasn't going to spend, I didn't plan to talk about because of time, but yes, the dark photon could be dark matter itself, and you could use the same experiments to search for that. And the kinematics is totally different because then you're looking at an absorption signal of the dark photon. So instead of this parabola for scattering, for absorption, you would actually be in the limit where you have very little momentum transfer because it's a non-relativistic particle and you have some finite energy transfer. So this is an aside, I guess. If you were looking at absorption, you would want to, your allowed phase space would basically be a point here. And that would be very different. But yeah, that's something you can still do with these experiments.
thank you.
Okay, so these two mediator limits for the dark photon have different implications for this cross section. So let me give this cross section definition a little more carefully because that's the part I went somewhat fast over last time. So this is a cross section, but what it really is you can think of it as some sort of momentum dependent potential between dark matter and target squared. You can think of it as secretly like that. And the way we often translate things for direct detection is we translate it in terms of a fiducial cross section instead of the full momentum dependent potential. So translating that to like a fiducial cross section, sigma E, this is momentum independent. And then we include a form factor, which is usually called the dark matter form factor. let me be specific. If this is an electron target, then I would call this sigma E and FDM squared. If it were a nuclear target, I might call it, it would just be sigma N. But for dark photon meteors, just for convention really, usually the constraints and searches are shown in terms of the dark matter electron cross section. So I'll just focus on this one. And so this fiducial cross section, I defined this last time. So it's basically picking a reference momentum for this cross section. And so the form factor contains all the momentum dependence itself.
So the form factor for an electron and nuclear target is we're using the same form factor?
Yeah, that's a good question. Actually, different form factors and conventions are used for nuclear and electron scattering. So for for electron scattering, this Q0, this reference momentum, is usually picked to be ME alpha, as I mentioned last time, and I'll go more into that. If this were a nuclear target, then usually just again for convention, but it makes some sense. You would pick the reference momentum to be the dark matter velocity times mass, and that's really because the expectation is when you have dark matter electron scattering, the lowest momentum scale is not going to, the lowest momentum transfer scale is not going to be set necessarily by the dark matter momentum, but by the momentum of the bound electrons. So that's often going to be setting a relevant momentum scale because, as well see shortly, when we're dealing with bound electrons, they're not momentum eigenstates, so we can think of them as having some spread, or equivalently as having a typical momentum in a material, which is going to be given by this alpha ME. And so that's why for electron scattering, this reference momentum is usually used because that sets the scale roughly of the problem. And for nuclear recoils, that doesn't really, this kind of argument doesn't apply, and just for convention, usually we set kind of the expectation from the dark matter kinematics for the momentum transfer, reference momentum transfer.
I guess I would expect it that. Sorry.
I guess I would expect to see for each of these form factors something more about the structure of the target. Like, I don't know if I have some dense nucleus versus some different type of nucleus. Is that kind of factored in what you're saying?
No, this is really just a kind of convention, I'd say, because the thing that matters is the thing we're trying to capture is depending on your mediator mass. If the mediator is very light, then you'll strongly favor lower momentum transfers. So in terms of like this plot, that means you'll strongly favor down here actually, which is not captured just by drawing this region. If you favor low Q, you'll favor down here. If you have a heavy mediator, you don't have so much preference for low Q, and actually because of the, just the Jacobian base space, you'll tend to favor large momentum transfers. So that's the important part. I'd say this choice of the reference momentum is a bit of just a convention to help compare different experiments, because definitely for a different target, that reference momentum will actually be quite different from where most of the signal is peaked, depending on what you're looking at.
Perfect, thank you.
Okay, so yeah, that's basically the point I wanted to get at and remind everyone of. we'll have these two different benchmarks which correspond to different mediator limits. And you'll see, therefore, in the literature, two cases generally. You'll see the case of this form factor being 1, which is the heavy mediator limit. So MD is just so massive, none of the Q, reference Q or Q dependence matters. Or you'll see the limits where the mediator mass is taken to 0. The other implication of that is if we, sorry, just keep switching, but if we go back to this kinematics plot, if we had a light mediator and we're favoring very low momentum transfer, so we're living down here, that also is implying we're favoring pretty low energy depositions. So if you have a light mediator, there's kind of multiple reasons to go to this low energy threshold target systems. One is that you have the light mediator itself favoring that. And of course, for the light mediator, you can have freeze-in where the dark matter mass is lower. That also means lower energies. Whereas for the heavy mediator case, you can be anywhere in here and there's just not as much of a preference for the lowest energy transfers, energy depositions. Okay, so that mostly covers everything on the dark matter side. And so now we can start getting into this structure factor side and different types of target systems. So let's start with the big question of why condensed matter systems have attracted a lot of attention in recent years. So this is a summary plot I made of a few different types of materials and excitations of materials you can look at to look for, in particular, this freeze-in candidate. So this is the light mediator case. So one simple answer you might give is just if you compare nuclear recoils and then you look at all the studies that have been done, you get kind of amazing sensitivity, potential sensitivity from looking at various condensed matter systems. For instance, here we have semiconductors of germanium and silicon. These are also semiconductors. They're various crystals. They're called polar crystals, but they're also semiconductor crystals. And these are looking at phonon excitations, which are lattice vibrations in the crystal. And very roughly, actually, you can stare at these different reach curves and kind of draw a line that looks like this. And that's scaling roughly as 1 over the dark matter mass. And that's just coming from the fact that as we get a lower dark matter mass, we have a much larger number density of dark matter. Of course, there's orders of magnitude, fluctuations about that, but that's roughly where the scaling is that you see go. And so as we're going lower in dark matter mass, comparing nuclear recoils to sub-GeV dark matter, where the energy scales are lower. So here we're talking at most keV energy scales, and here at most EV, just from the dark matter kinetic energy. Aside from the fact that we have sensitivity, we need to consider bound or condensed systems. So what I mean by that is it's in particular in this mass range where we're going from the keV energies to EV energies. And for direct detection, we often want to have a lot of target mass. So if you have a bunch of target mass, it's typically not really going to be described by a gas of free particles. We don't have just a gas of free electrons. And the typical energy scale of bound electrons in materials is going to be around EV, tens of EV in this range. So whether or not we like it, we have to consider bound or condensed matter systems when we start to look in this energy range. But there are also advantages. So the other is related to this fact of kinematic matching. So even just ignoring the fact that we don't have these hypothetical free particles sitting around, the kinematic matching will be better for bound systems, by which I mean atomic, molecular, solid state, or just condensed matter, let's say. And so that's why this sensitivity does end up being as good as it is, because there is good kinematic matching. Yes, question?
I think that's all this first maybe.
Oh.
Actually, so the dashed lines are projections and the solid lines are actual constraints, or are both projections?
These are all projections. So shaded regions are actual constraints.
Okay.
And then the nuclear recoils is, I don't remember, I think a 10-year projection. And then these, so that's another thing. These nuclear recoils are 10-year projections for 10-year experiments. And these projections are actually for much smaller experiments. These are for kilogram year exposures. So these are kilogram scale experiments.
And the freezing band is the favored region for this production mechanism. No? So if these constraints were real, then how could you produce that matter?
That's right. This is the predicted cross section if you take that freeze-in abundance and you require the freeze-in abundance to equal the observed dark matter abundance. So that's where you would want to live. And so, yeah, indeed, if you had a kilogram experiment, that would be way beyond what you need actually to see this with zero background, of course, with the caveat. So this is saying with the sub-GeV dark matter, even with pretty small experiments, as Jody already mentioned, like gram, 100 grams, that would potentially be below these
We are
interesting
very
relics.
close to test the freezing mechanism.
Yeah, we are actually very close. I think Jody showed a plot. Yeah.
That's very interesting.
Yeah. Yes.
So Jody also talked about in her lectures how for instance, like the noble gas experiments, the best kinematic matching comes when you match the dark matter mass and the mass of the nuclei.
Mhm.
In these condensed matter systems, are we matching masses in a similar way?
No, we're matching. So I was going to talk about that next. We're matching available excitations in the condensed matter system with the momentum and energy for the dark matter.
Got it. Okay, thank you.
So about electron excitation, sorry. What is it about silicon that would make it like a bit more sensitive than germanium?
Right. So silicon has a actually, I don't remember why silicon. Sorry, I had an initial answer and then I realized it may be off. I don't remember why there's a slight difference. I think it has to do with, okay, sorry, I remember. So it's because of the way we're talking about the rate per target mass. So kind of the way I would think about it is silicon, you can really only scatter off the outer few electrons. Silicon is a lower mass nucleus with 4 valence electrons. Germanium is a much heavier nucleus with 4 valence electrons. So per like mass that you get more electrons from silicon. I think this would explain most of it.
Okay.
But yeah,
Okay, thanks.
Hi, so what exactly is on the vertical axis? It's the scattering cross section of dark matter.
Oh, yes, yeah, thank you for, yeah, this is the sigma E, the fiducial cross section that I defined
Oh, because I remember that for Xenon 1 ton, the excretion at 30-40 GeV is all the way down to 10 to the power minus 37 centimeters squared per nucleon.
You mean it should be a little bit lower here? Is that what you're?
Yeah, it's a lot lower.
A lot lower.
Yeah.
Uh,
47, sorry. Yeah, 10 to the power minus 47.
47, but that's for the, okay, that's because I'm plotting this in terms of the electron scattering cross-section. So you're right for the, for the usual plots for sigma n, for xenon 1 ton, absolutely, it should be less than like 10 to the minus 47 centimeters squared. But this is the electron scattering cross-section, and there's
because the dotted line says nuclear recoils, but then vertical axis says it's electron.
Yeah, there's a relative factor of mu. There's a relative factor of basically the proton mass over the electron mass squared in the definitions of the two cross sections. That's why it looks so small here. So going back to this slide. So there's the way we define these cross sections is with the reduced mass squared. And this will be roughly the electron mass squared. But when you do it with the nuclear recoils, this is roughly the proton mass squared. So there's a huge factor like 10 to the 7 or whatever, 10 to the 6, 10 to the 7 that appears when you normalize to the same, or when you translate it to electron scattering for the same model.
Okay,
Yeah.
cool. Thank you.
Maybe in each question, but do we have to care about neutrino background in this case?
Oh yeah, that's a good question for neutrino background. There have been some studies of neutrino backgrounds. They're one sort of maybe trickier thing with modeling them so far is that a lot of these proposals are still new, and it depends on exactly what you're detecting in a particular experiment, what the relevant neutrino background is. But one interesting thing is like for these experiments, typically the benchmark proposal is like a kilogram scale experiment. And for those, the neutrino background is not expected to be very large. So as we see with like xenon, they're hitting very solar neutrino backgrounds, but that's for much larger exposures. And so when we're still talking about kilogram year exposures, then for instance, solar neutrinos is either an order 1 of events per in that time frame, or very, depending on what you detect, not a very big background for that exposure, either negligible or not big.
Okay, thank you.
I have a question mostly on the shape of the curves. I would have thought that based on the previous plot, where you have like the q squared over 2m, that there would be specific masses where you get like peaks in this curve that you'd be the most sensitive to. I guess I'm just not sure why you get this this overall shape for the curve.
Yeah, so that's a good question, why all of these have this shape. So all of them kind of have this shape because they all do have like a peak kinematic matching. So you'll get the best sensitivity when you get like the best kinematic matching between your system. So here that makes sense. It's going to be around, I guess, well, it's like 20. I don't know. I guess it's like 20 here. Around peak kinematic matching. It's not exact here clearly. And below that, you're set by a threshold of your system, either your system or your experiment. And then above, you're always going to be set by the dark matter number density. So you're right that there is kind of a peak, and that is corresponding to the best like matching. So in all these cases, and then the behavior around that is always the same, threshold and number density.
Okay, so it's a slow fall off from the peak. It's not like a resonant peak.
Yeah.
Okay.
Yeah.
Thanks.
Exactly. Okay, great question. So let me now give some examples of what that kinematic matching looks like. All right, so let me draw again this parabola. And for say MeV scale dark matter, so just take M chi to be MeV, then we're talking about roughly KeV momentum transfers and EV energies, order one numbers here. And of course, if we had a free electron exactly at rest and we could scatter off that, that would be perfect kinematic matching, just like in the nuclear recoil case. But we don't, we have these electrons in various bound systems. And we can compare now this kinematic region with allowed types of excitations you can have in the bound systems, which won't have a resonant response in general. Actually, there's a few cases where there's a resonant response, but there's not necessarily one. And instead, there's kind of a broad response that will be peaked at typical momentum and energy values. So, well, starting with atomic systems, well, we already talked about just recoiling off the atom as a whole. That's the nuclear recoil. But these blue is basically electron excitations in this color coding. But with the xenon liquid noble experiments in general, you can look for ionization of the atom. And so the typical threshold energy or energy deposition scale for omega is just set by alpha squared ME around 10 eV. So that, for instance, is the ionization energy for, well, it's close to the ionization energy for xenon, or like 12. And the momentum transfer is going to be also set by the wave functions of these bound electrons, which again, for the outer shell electrons, you can just think of it as like a hydrogen-like atom with the outer shell electron. And that's going to be set by this, by the inverse of the Bohr radius, or about 4 keV. So we immediately see that these scales are pretty well matched in principle to the kinematic phase space for MeV scale dark matter. Okay, so that's sort of why I've drawn this roughly to be relevant in the mass range. It's actually a little higher, more like 10 MeV to GeV, because this is 10 eV. As atoms get closer together, basically the energy levels of electrons in the material can get moved around, and they can actually get lowered. So if we go from atoms to molecules, then generally we'll get lower energy excitations. And as we go to even more condensed systems, condensed matter systems, they go even lower. So that's why I have basically these going lower in dark matter mass. So turning next to a molecular system, that's pretty similar to atomic systems, but because you might have, just because you're bringing a bunch of atoms close together, you might be able to reduce some of the electronic states. You might also be able to look at excitations in the molecule as opposed to just ionizations. So that means exciting an electron from one bound state to another. In some cases, you'll get some scintillation light from that.
That was
Okay, yeah. Yeah, so for xenon, you would be detecting the electron coming out and being drifted in the TPC. There's proposals for some molecular systems where you could detect the excitation because it leads to some scintillation in the material. So because of that, the typical momentum scale is similar for the response, but the typical energy scale can be a little bit lower. So I've drawn this down to about 1 MeV instead. And then when you go to condensed matter systems, having a lattice of atoms, then there's a lot more freedom in terms of what the possible excitation, the energy levels of electrons are, and what the gap to excitations are. So now I've just extended it all the way down, down here, because as an example, you could have a metal, and a metal, there's actually no gap for creating an excitation in the metal. So the gap, the threshold for the excitation of the material could, in principle, be 0. Practice a metal is not a proposed experiment because it would be very hard to detect excitations in a metal because you produce them, but then they go away very quickly. But indeed, you could have semiconductors, which would be, usually these are kind of, say, EV scale gap. So that would allow you to look for MEV dark matter and above. And then aside from metals, then other materials are being proposed like superconductors, dark materials. And the basic difference is they just have a loud energy, they have an energy threshold for these excitations, which is as low as, say, milli-EV in some of them. Yes.
What are direct materials?
They're a special exotic material with like a special exotic just like band structure basically, but it's not too important for for this discussion. Okay, so that's for if you're looking for dark matter electron scattering, and the orange blobs I'm showing are different kinds of excitations you could try to match onto if you're interested in dark matter nucleus interactions, so say dark matter nucleus interactions. So instead of thinking of free nuclear recoils, what will happen instead is, say you have 2 bound atoms in a molecule. What you can do is you can break the bond in the molecule, and that will have a typical energy threshold. You need at least 10 or tens of EV in order to break a bond between the 2 nuclei. And so that's something that people propose looking for that would be relevant for, again, these somewhat higher dark matter masses. If you have a lattice of atoms in a solid state material, again, if you deposit like, say, 20 EV, 50 EV of energy, that can be enough to kick an ion or an atom out from its site in the lattice, and it creates a defect in your lattice, and that's something you could look for. So that's another proposal, bond breaking in solid state materials. As you go even lower, the nuclei are very far from free. We really think of these nuclei as being kind of in harmonic potentials. So you can kind of think of, for instance, if you're in a solid state material, think of each nucleus as sitting in a kind of harmonic potential generated by everything else in the crystal. And instead of, and so when dark matter comes in and kicks a nucleus, what we're really exciting are vibrational modes, or what are called phonons in the condensed matter system. So for instance, if you have a molecular system, you might just directly excite this vibrational mode with a typical energy of 0.1 to 1 EV. And if you're in a solid state material, you can, the vibrational modes go to even lower energies because you actually have Goldstone bosons, so they actually go to 0 energy. And these will usually be below about 0.2 EV. Okay, so the summary is that this is one reason condensed matter systems are so interesting, because they provide all these different kinds of modes. You can basically, the dark matter can come and probe at different mass ranges. For different ranges of dark matter mass, you'll be able to probe different excitations in these systems. Yes?
Could you say again what you meant by you have Goldstone bosons in the last thing that you said?
Yeah, so for the solid state material, because the atoms are in this lattice, you're actually breaking translational symmetry. So you get these acoustic phonons, which have a linear dispersion with the speed of sound. So you start off, of course, with a translation invariant system, but then the ground state breaks it by putting them in this lattice. And so, yeah, you get 3 acoustic phonons, linear dispersion.
I probably missed this, but what do we mean by the difference in molecular systems versus condensed matter systems?
It's not that much other than molecular systems I might just consider like a molecule with 2 or 3 or even tens of atoms, and condensed matter I really mean 10 to the 23 or something.
Right.
All right, so this shows that there is a potential for good kinematic matching, some maybe dark matter. There's a bunch of other considerations, of course, want to have. So I've already mentioned a couple of these, but let me write them down again. So one is, I've been talking about the thresholds for the excitation itself. So that I'm saying, here's a threshold for for a vibrational mode. But just to give a sense of the current status, how close are we to achieving those kinds of thresholds? I'll just mention for electron excitations, there's xenon experiments with single electron thresholds, about 12 eV already, as well as the semiconductor experiments, currently able to achieve similar thresholds, eV already. So we're already at the stage where we can get to very low thresholds through a lot of progress in recent years. For nuclear recoils, this is electron, the case is a little bit harder. So I said in principle, we can get to very low energy vibrational modes. And for xenon, right now, we're talking about, of course, for nuclear recoils, it's quite high, keV. But there's also lots of work in getting to lower thresholds. So I think I talked about CRUST-3 as an experiment. Make sure I have the number right. So for nuclear recoils, it's a bit farther off. Right now, the best experiment is around 30 eV for threshold. So if we want to get to the kinds of single phonon things, that's going to take longer, basically. Another is exposures, and we've already talked a little bit about that, which is that you don't need very large exposures in order to get at very interesting perimeter space. And go back to xenon, 10, that was 15 kilogram days. And some of the semiconductor ones are like 1 to 200 gram days. And they're already, as we'll see, they're already not too far off from the Friesen line, for instance. So this is promising so far. A big question is going to be backgrounds. And here there's a lot of uncertainty because the known backgrounds can be estimated, of course, and they're not very large, but there's a lot of, there's expected to be plenty of surprises as we keep going in this direction. And so there's a lot of uncertainty on potential unknown backgrounds that may crop up. And indeed, in the experiments we've seen so far, there's already, initially, there was already a pretty large background in these types of experiments. There's now work in understanding them better and ways to mitigate them, but certainly the first versions of these searches that have been done show that there was a very large background that wasn't initially understood. So I'll just put lots of unknowns as we go to lower energies. One reason condensed matter targets have attracted attention is there's a possibility of trying to distinguish signal and background with an additional technique of directional detection. So the idea is if you're looking at a crystal, it might be a pretty anisotropic crystal, meaning that this response function will actually vary a lot depending on whether you're talking about momentum transfer, say, along the crystal direction or perpendicular to it. So as the Earth is rotating, as the Earth is rotating, the dark matter wind is going to come along particular directions in the crystal. And you should see some modulation in the rates if it's really a dark matter signal, which is corresponding to the Earth's rotation. This is a daily modulation. So this is one cool aspect that could be used if there's any signal to try to help distinguish it from backgrounds. Yes.
Just kind of a general question about this directional detection. So like if you have a light dark matter particle coming in and there's an excitation and a photon or a phonon comes out of the excitation, is there some prediction or probability distribution of which way that phonon will be going, or how does that directional detection work?
So the primary phonon, so everything I'm talking about is like in terms of target response, is the primary response, meaning like the immediate response of the target system. But usually that's not the thing that's being detected. So similar to all the subtleties Jody was talking about, you have to model how that primary thing turns into the secondary excitations that are detected. So usually the direction, it's may not be true 100% of cases, but usually any directional information in the primary signal itself would be difficult for, say, a phonon signal. So really the directionality is coming from the fact that the response of the target varies as it rotates relative to the dark matter wind. So the rate that you see should be varying.
Can you sort of like clarify these exposure values that you wrote? Like, is that xenon 10? 10 is what, like
10, yeah, 10 is referring to the generation when they had about 10 kilograms of xenon.
Oh, okay,
Yeah.
I see. Because I mean, I think like, for example, for semiconductor detectors, that kind of value is like more representative of, for example, the electron recoil searches than it might be, for example, wind search for a wind search.
Yeah, so it's a interesting thing. I actually have a plot later. Maybe I can just jump ahead. All right, here we go. So this is it's an interesting thing for xenon 10. It's actually giving better limits than xenon 100 for the light mediator model. That's what's shown here. So that's what this means, light mediator model. And that's because it turns out that experiment had a very low threshold down to single electron events. And it was actually harder to do single electron searches with the later generation of xenon detectors. So even though this was pretty early and the exposure is not very high, it's actually, at least for this model, it's giving the strongest limits. That was your, like, why am I talking about xenon 10 versus?
I see. Okay, then.
I was wondering if on the previous slide you were on, you said you get some directional information from the primary interaction, but if you have like subsequent interactions, can you then get more directional information, like maybe like a smaller angular resolution? You have multiple hits of the crystals.
So I think it's hard to get directional information from the observed signal. Yeah, because the timescales are, the timescale for this primary thing to turn into secondary things is quite fast. I don't know of any specific examples where one can do that. Well, there might be some. So yeah, there might be some in that. So yeah, maybe I can just say a little bit more, like if I take a semiconductor and I excite an electron, the electron will scatter again against other electrons. It'll create a whole bunch of things, electrons and phonons. And those electrons, you could either detect the electrons or the phonons in the situation. And because you've created a whole shower of particles, it's hard to get information about the primary one. But it might be possible in some like very special cases. So if, say, for instance, you produce an electron, but it's like so close to the band gap that it actually doesn't scatter again very much, then that actually might contain some information because it doesn't scatter again very much about what happened. But for higher energy stuff, I think it's quite hard.
All right, thanks.
Okay, so I have too many slides. So in the interest of time, I'm going to skip ahead and go to these pictures of the.
You have an extra half an hour.
Yes,
If you
but I have too many slides for half an hour.
Too many, sorry.
Too many, yeah. Okay, so let me give another way of thinking about this, which is just a more visual way of talking about this target response. So this is, again, the same parabola, just in log space. And these are the different allowed regions for different dark matter masses. One line I'll draw sometimes in these plots is this line here. So if you see, all of them have to be below this line here. And this is basically the line omega equals QV. If you remember, the individual parabolas were QV minus Q squared over 2x. Okay, so no matter what the dark matter mass is, you're going to have to be below this hard cutoff. And then, depending on the dark matter mass, you'll be even more restricted. So I want to compare these allowed scattering regions with the kind of responses that we'll see. And this will give a more visual representation of what the response looks like. So now I'm overlaying a possible response for dark matter electron scattering. When the momentum is very high and, when the momentum transfer is high and the energy deposition is high, like we're basically in this region, the response will converge to the resonant response, which is free particle scattering, right? At sufficiently high energy momentum scales, it doesn't matter that the electron is bound, so you should get this resonant response. As you go lower in momentum, this is the fact that I've been saying, which is that we need to consider the bound nature of the electrons. And so this response will broaden as the momentum scale reaches this typical alpha ME scale for the wave function of electrons. So this is 1 over radius. And then what you'll see is you'll get kind of a broad diffuse response down here. And depending on what you're looking for, it'll get cut off at some threshold. So this will be some broad response. And if you're looking for atomic ionizations, it'll get cut off at around 10 eV. If you're looking at semiconductors, it'll get cut off around here. And then Dirac material superconductors down here. If you're looking for dark matter nucleus scattering, so this is the picture instead, at very high energies and momentums, again, we get the resonant response for the free nuclear recoils. And as we go lower, this energy scale I've indicated here is the bond breaking energy. And so as you approach that, again, you'll get a broadening of the response. It'll become actually really broad here in what's sometimes what I'll call the multi-phonon regime. So this is kind of an interesting regime where you don't really think of it as scattering off individual vibrational modes. You also don't think of it as nuclear recoil, but instead you have a probability of creating like very highly excited vibrational modes. So that's what's happening here. And then for dark matter nucleus scattering, you actually have a resonant response down here, either at either a resonant response on the optical phonon energy or a resonant response on the acoustic phonons for solid state materials. So this would be, for instance, a resonant response on a particular omega 0, and I've just indicated a band of possible energies. Yes.
Aside from the momentum transfer potentially being higher, in the case of warm dark matter, does the target response change at all?
No, so yeah, I'm trying to decouple the two and just talk about target response independently of whatever the probe is, which, yeah, it could be dark matter, any dark matter candidate, could even be a standard model candidate or particle. So it's, yeah, it's mainly just how does your probe push you in certain momentum regimes? Yeah.
Yeah, so can you expand a bit on these like diagonal sort of resonance regions? Because like for me, it makes sense when you talk, for example, the optical phonon region, like, you know, as a resonance, but not too clear why you would have it like in a diagonal space.
Yeah, so you mean the acoustic?
Oh,
phonons?
yeah, but even in the previous plot, I think you had something similar. Yeah, this like green region.
Oh, the green region is just, well, at very high energies, it's just the free electron dispersion. So it's similar to when we're doing, well, when we're looking at free nuclear recoils, I was saying there's a resonant response at the free nuclear dispersion here.
So like above that value ED.
Yeah.
Okay. And so that would mean that there's like sort of interactions with an energy above that are just very likely.
If you're looking at interactions in here, it looks exactly like it's a free particle. It doesn't matter that it's
I
bound.
see.
Yeah.
And what about acoustic phonons instead?
Yeah, so this scale here, this is around keV or a few keV, and this is roughly set by the lattice spacing of atoms in solid state material. So if you have a crystal, then if you're looking at really high momentum transfers, you can't really tell that there's all these atoms together because you're probing such short length scales. So you're kind of scattering off of individual nuclei up here. But if you're talking about really long wavelength momentum transfers, then you can kind of think of dark matter, kind of, there's a potential like this, and you should actually be sensitive to kind of all these different, you should be sensitive to all of the atoms in the lattice. So that's setting the scale here, below which you are actually able to excite these collective motions of the atoms in the lattice. So for instance, like an acoustic phonon would be like the mode where all of them move together with a slow modulation.
Okay, but so just to make sure I understand the plot correctly, the green band is where you would have this excitation.
Yeah, so let me write that down. So the acoustic phonon has this dispersion, linear dispersion. So that's what I'm drawing here. And yeah, if you, what happens is if you're able to deposit this Q and omega, you can create one acoustic phonon.
Okay.
With exactly the dispersion in the material.
Okay, thanks.
Okay, so what these two figures are trying to illustrate is certainly for electron scattering, is just showing this kind of overlap of phase space and response. And also for dark matter nucleus scattering, it's showing once we're below sub MeV dark matter, is 1 MeV, the space, the kinematic region, then the thing that you can do is you can have resonant excitations into these phonons in a solid state material. Whereas if you're considering heavier dark matter, then you're actually in this kind of weird region where you're exciting a nucleus in a bound potential. All right, so let me give a more practical, more quantitative example with the hydrogen atom, dark matter electron scattering. So just to be a little bit more concrete now. So this is still quite simplifying that I'm not dealing with the whole many body physics, but I think it's a nice illustrative example. So this was the definition of the structure factor. When I'm dealing with the ionization of hydrogen atoms, I can treat all the atoms independently. So this is just going to be scale as a number of atoms. This is just the number density. And so if I were looking at this dark photon interaction, it would lead to this kind of structure factor, to be more concrete. So this part is coming from the interaction between, so when we have the interaction potential between dark matter and a charged particle, it would look something like this charged particle, say, as we talked about for the Coulomb-like potential. And so when we factorize things into the structure factor, the only part that matters for computing the target response is this UVI Q.R. And so that's why I can just focus on that piece here. Yes.
And even though we're only looking at electron scattering, we also need to include the contribution from, I'm guessing N is the nucleus?
Yes, I've included it, but actually, yeah, in general, it's there, but it's negligible because, yeah, we're just looking at ionization and it's very, the nucleus is very heavy, so it's not really relevant. Yeah. And this is hydrogen, so I can avoid this complication of different electrons, just leave one electron. So that really simplifies to basically one matrix element that we need to compute. So the sum over final states for unbound electrons, these are labeled by the outgoing momentum. So this turns into an integral over outgoing momentum. So this is an asymptotic momentum. So let's say you excite this electron, and then once it's very, very far away from the nucleus, it'll have momentum k with energy k squared over 2 ME. So you can think of this, it's basically looking, so k looks like a plane wave very far away. The initial energies is 13.6. So this is a nice example because it's mostly, well, it is solvable. Actually, writing down these outgoing states is more complicated than you might think. We know the initial state, so we have that one. That's just the ground state hydrogen. So you can use the known solution where A naught again is the Bohr radius. So that's why I've been talking about that length scale. And so there was a paper a few years ago that looked carefully at these outgoing states for various reasons in the literature. You can often find tabulated wave functions for bound states. Of course, we know them for hydrogen, but you can also find numerical bound states for numerical wave functions for bound states of other atoms as well, more complicated atoms. But it's not so common to find them for the outgoing states. You need to resolve, basically, you need to resolve the system. So using the correct outgoing states, I'll show you the result for this dynamic structure factor. So this is basically, this is log of the dynamic structure factor. And it's a contour plot or 2D plot. So we have the highest response of the hydrogen atom here. And in fact, you see this strongest response is following this line, which is actually converging to the free electron response at very high energies. So it's quite sharp. Well, it's relatively sharply peaked. It's going to get more and more sharply peaked as we go to higher Q and omega. This is cut off at the threshold for ionizations. If you were able to detect excitations, you could in principle look down here, but assuming liquid no bowl experiment, then you're cut off at this point. So just kind of dimensionally, you can see that everything is kind of alpha ME or alpha. Things can be determined in terms of alpha and alpha ME. So if you go through this, and I give the full expression in the notes, I believe, you can see that this can be estimated just in terms of alpha ME squared over alpha, which allows you to get an estimate of the rates. Okay, and so this is what I mean by having kind of this broad diffuse response down here. So there is a peak, but it's kind of broad down here. But this dashed line shows you the allowed. So this is the line omega equals QB. So this dashed line is actually the upper bound of all those parabolas I was showing. So if you have halo dark matter scattering, you have to live in this region below the dashed line. Yes.
I know that you said this before, but could you repeat what that is, please? Why I have to live in that region below?
So yeah, let me just go back to this plot. That's coming just from this line, basically.
Okay.
Yeah. So all of them follow this inverse parabola, and then so all of them have to follow the omega equals less than QB.
Okay.
Yeah.
Thanks.
So what we actually learned from this example is that naively, it does seem like atomic targets are good in terms of the Q and omega lengths, Q and omega scales you start off by estimating, but actually it's not so ideal because the peak of the response of this system is here, but dark matter scattering has to be down here. So you're actually down by a few orders of magnitude when you're restricted to this region of phase space. So I would say atomic targets are not quite ideal. Just in terms of the theoretical matching. Kinematic matching. Yes, question?
Fine, I can speak up.
Oh.
Shout the mic.
Yeah, I'll repeat it.
So by atomic target here, you mean like, for example, a gas or something like that, right?
That's right. So I'm treating this as a gas of hydrogen atoms. And if you were to take, say, liquid xenon, it's not really a gas, but it should be a pretty good approximation because the effects of it being a liquid versus a gas are not too large, but they're hard to compute, but they're not too large on the energy levels of the electrons. Yeah. All right, so given this fact that atomic targets are not quite ideal, let's now look at semiconductor targets, which are where there's a lot of action these days. And so this is the structure factor computed for silicon semiconductor from a paper I worked on with some collaborators. So it's very similar, but there's a number of differences. So this, first of all, this dashed line is the same. Kinematic limit, we have to live below this line for halo dark matter scattering. The gap for excitations is more like EV in a semiconductor, and so that's why this response function now is being plotted to much lower energies. At high Q and omega, you're again going to be peaked around this free electron dispersion, Q squared over 2me up here. It's somewhat broader than before, but if you keep going, and again, it'll be sharply peaked around this free electron response. And then there's one interesting feature both at lower momentum, which is that there's a new mode that appears in these systems, which is called a plasmon. So plasmon is a collective excitation of electrons. And at zero momentum, like this energy is just the classical plasma frequency. So this gives an example of a kind of emergent many body effects that you might see in these condensed matter systems. And so the response will actually be peaked around where this plasmon dispersion is. So it's almost like a resonant response of the system to create a plasmon, though it's not. It's actually a quite broad resonance. So this is a unique feature, though it's not actually accessed in terms of dark matter scattering because you're restricted down here. Okay, but what we learned from this is that semiconductors are somewhat better in terms of targets if we look at this kinematic matching, because yes, it's still the semiconductor response is still peaked outside of where the dark matter scattering happens. But the response is somewhat broader and you still get a lot of large response down here, which is what we care about. Yes?
I can also speak up.
So this plasma response, can you move this a bit depending on the semiconductor you choose, or is it generally the same?
Yeah, you can move it a bit. For kind of conventional semiconductors, it doesn't move too much, so it's kind of moves like up and down here. There has been a proposal to look at some exotic materials where you really move it really far down, like maybe even as far down into this region, like suppose I could put the plasmon down here. But those are kind of exotic, and it's hard to get it to be as resonant as it is when it's up here, as far as I've seen. Just because, yeah, it's kind of hard to, I think they look at materials where there's really an effective electron mass in the material, and they try to make you can look at some exotic materials where the effective electron mass is really large and you lower this. So. Okay, so the summary is semiconductors are somewhat better for the lower gap, somewhat better. So they're not ideal, but still, as we see, we don't really need ideal when we have many orders of magnitude between kilogram scale experiments and the thermal relic lines. So in the last few minutes, I want to say a little bit more about the experimental status. Some of this was already covered by Jody, but this is a reminder. So to put this on more concrete terms, this discussion is really focused on a way to think about all these different materials in terms of their response functions and what's ideal, what's good kinematic matching for a given dark matter target. So let's just look at how in practice these are being used. So we already looked at this plot briefly. So for the atomic targets, this approach is being taken by xenon TPC experiments, where the signal is the electron being produced. So there's an atom being ionized, the electron is produced, and then it's drifted. This is the S2 signal. So this is also called S2 only signal. And for a while, these were giving actually the best constraints on dark matter electron scattering. So this is coming from this earlier paper. And yeah, for a while, this xenon 10 was actually one of the best constraints in this massless mediator case. But a lot has changed. So now we have these semiconductor experiments. So one class of experiments is using silicon CCDs. So here the dark matter comes in and it excites an electron. So what happens is there's an electron and there's an absence of an electron, the hole, and there's a voltage applied so that the electron can be, again, drifted. And this is read out multiple times actually for the skipper CCD. So this graphic actually shows an example of that single electron in 1 pixel of this CCD. So it's basically a camera able to detect 1 electron in a given pixel. So this is a really interesting technology that is being scaled up right now. And basically they can sit and wait underground for a few hours and just see how many pixels are lit up in an isolated environment. The other kind of technology is the one that Jody already talked about quite a bit. So instead of looking for the electron itself, applying a very high voltage and looking for all the radiated phonons from the electron, resulting in these peaks in the phonon energy when you have 1 electron, 2 electrons, 3 electrons. So yeah, I should just mention again, the 1, 2, and 3 electron thing is these are the secondary electrons. So they're not the primary electron. Primary electron interacts a bunch and you get all these secondary ones which are being detected. Okay, so that leads to this kind of plot with lots of different constraints. Again, this is for the massless meter, just for convention. I'm just showing the same every time. So as I was saying, for a while, xenon 10 was the strongest for this model in a particular mass range, and that's this limit. And now we're actually seeing the semiconductor experiments catching up. So this is the CCD experiment, Sensei, which is just below it now. We're not very far off from the Friesen line, actually. And this is, I don't remember the exact number, but the exposure is not very large. It's less than, it's probably around 100 gram days or 10 gram days. Okay, order of magnitude there. So this exposure is actually, yeah, not very large. And there are plans to, of course, keep scaling that up to kilogram or even 10 kilogram scale. Oh,
Yeah.
yeah.
So actually I can say for the dynamic line, which is just the one on the left.
Yeah.
The exposure is 100 grams per day. But no, what I wanted to know is, can you, I know you read this, but I still don't know exactly. Can you talk more about the freezing line?
Yeah, oh yeah, so the question is about the Friesen line. You mean where is it coming from? Or?
Yeah.
Yeah, so the Friesen line was basically coming from this process where E plus E minus through this vector goes to dark matter pair in the early universe. So if you calculate this process and you require it to give the right relic abundance, it requires the combination of this couplings. So this one, well, the combination of couplings is the kinetic mixing charge and G chi. It requires that combination to be about 10 minus, I don't know, 13. I might be off by an order of magnitude. So it requires that combination of couplings to be something in order for this process to give the relic abundance. And the same combination appears inside the cross-section definition for the light mediator. This is the cross-section definition. So you can just plug that in, and that's what's giving this line.
Practical level. Okay, so like that is the value that we would expect from like for freezing production. I guess I'm wondering like what would it mean when experiments like will go past this line?
Oh, yeah, so this is only one benchmark. There's other possible benchmarks. So if you were just talking about Friesen itself, you don't, what it would just mean is that you would get a subcomponent of dark matter. If you were to go below with smaller couplings, then less dark matter is produced and it would be a subcomponent. But there are other models that live in this parameter space. I guess sometimes maybe it seems like this is the only model, but it's not. There's other parameter space. It just doesn't give, it doesn't always give a line. So people don't, it's more like a big shaded region of other possible models. Yeah.
Okay.
So you're allowed to be on this line or band, right? It's not like
Yeah, the question is, are we allowed to be on this band or?
no, it's like so the constraint of Friesen is that if this thing is true, you will lie on the band, not like above the band.
Right, so the question is for Friesen, would we lie on the band and not above? And yeah, we would be exactly on the band for Friesen, yeah. If you were above, that would also be bad. You would have too much dark matter.
So sorry, is there a reference where I can see like how big this band can be? Like you know, tons of
If there's a reference, yeah, where yeah, we can talk about that after because yeah, we're very low on time. So I will let you go to lunch with the last slide, which is just to say there are lots of other materials we can maybe talk about in the discussion, other proposals for experiments, and these are kind of the this was the status plot. This was the plot showing lots of optimistic projections with other materials. And hopefully this gives you a sense of where some of these projections are coming from, but I'll stop there so that we're on time. Thank you.